Well, hello and welcome to probably the last video of this series. So in this video we're going to be processing the final data and feeding that to the different models, baseline models and the deep learning model that we have created, and then we will evaluate the results that it produces, and we will plot the results as well. So let's just get started with it. We already have a function for evaluation of the model, so let's create another function for backtesting where we will be plotting the data. So we will create backtest strategy. We will pass y test, y pred, the predicted values, and the ticker name there. So linear regression model does not directly provide us the time series as an output of the prediction. It does provide us as a sort of an array, so we need to flatten that out to make that sort of a time series. So we will put a condition there: if is instance is y pred, which is the predicted value provided by the model, is pd dot series. We want to keep it as it is because it is already a series. So y pred series equals to y pred, but if it is not, we want to y pred series equals to pd dot series y pred dot flatten, and index is going to be y test dot index to keep the timestamps as per the training, the testing data initially that we had. Sorry, this function is still all right. After we make sure that the prediction series is the time series, is the series, we can plot. We already have imported matplotlib as plt, so plt dot figure fig size, it's gonna be 12 by 6, plt dot plot y test index for y tests, and label is gonna be actual. This is gonna be the actual data, not predicted, and color, let's say blue. Same way we want to plot the predicted values: plt dot plot y pred series, which is going to be a series of predicted values provided by the model, dot index y pred series. Label is going to be predicted, and the color red. Plt dot x label, the x-axis label is going to be time. Plt dot y label, y-axis label is going to be log returns, because we will be predicting log returns. That's going to be our target variable. Let's give a nice title to the plot: plt dot the title. We have the asset name, the ticker model backtest performance there, and plt.legend to show the legends, and plt.show to eventually show the plot. So that's going to be our backtest strategy. We are missing the parentheses somewhere. We don't need that. Yeah. Okay, so now the next thing is I want to show you, we have two different types of data. One is the stock market data for Apple, and the second is macro indicator data, right? The stock market data looks like this. I do not want to pre-process just yet, so I'm gonna get rid of those functions. Let me run everything from beginning to have a new memory instead of all the processed data already. So I'm not gonna run the create feature functions just yet, not gonna pre-process the data just yet. I do not want this as well just yet. So instead of fetch data, I'm gonna name it stock market data like this, and is it not ticker? What's the error? Wait a minute, let me check out the fetch data function. Data, high, low, and returning the data. Right. So stock data is ticker, ticker, ticker the upper. Wait a minute. And let me print stock data like this. Right, there it is. And if I pass in, yeah, so this is the data frame that the stock data that we are fetching. Let me run this RIMA, the evaluation functions, LSTM building, and backtest strategy. So now what I wanted to show you, let me bring this cell down here. And what I wanted to show you, we have stock data, then we are gonna have macro indicator data. Let me fetch that as well. Macro data, the function for that is fetch macro data, and we'll pass macro indicators there. And let's print that. So what I want to show you, we want to eventually merge this data with this stock data before we pre-process those. But the thing is, look at the date column of this stock data. The time zone of that and the time zone of this data are different, so we can't really do a left joint on date column directly, right? So and on top of that, we have macro data as the dictionary of different data frames. So let's process that first, so that we have run the data frames separately, and then we have the uniform date format as well. So let's first of all create an empty list tidy series, because we want to have a tidy up series. Let's do for loop through the dictionary of that macro data for name and df or series in macro data dot items. So we want to fetch series of data frame or series, and we want to squeeze that dot rename it to the name of that series. For example, in the first case it's going to be GDP and so on and so forth. Dot to frame, we want to convert that series to data frame. So that's one thing. Then we want to have index of all those data frame same. So s dot index is going to be pd dot to date time s dot index dot time zone to localize the time zone and that, and then we will one by one append that to tidy series dot append s. So we have a list of the different macro data series, and now we want to convert that list to a data frame. So macro df is going to be pd.concat tidy series, and we want to merge on axis 1 and dot sort index. So we keep the time sequence as it is. Now let me print macro df so that you have a better idea of what we did. Wait, let me just double check. Why is it being empty? It's not even it is in dot info. Why is it not returning anything? Yeah, there it is. Sorry, I didn't know what happened there. So now we have all the data in one data frame with one date column and different macro indicators as a different column. But if you observe GDP, the data for GDP is not available every month. It's quarterly data, while all of the data are monthly data, right? And there are more null values all over the data frame. So we will solve that. That's why I didn't want to pre-process the Yahoo data. First, we will pre-process all the data for removing those null values after merging those two. Now we have Yahoo data frame, stock data, and the macro data frame here. Still the date format, date time zone are different, so we will merge those two data frame, and we will keep the one date format for both of those. So let's do that. So stock data dot index is the date for them, equals to pd dot to date time stock data dot index is the date time column there, dot tz localize time zone localize none. And the same way we want to do macro df dot index, which is the date column there again. So pd dot to date time. I'm just gonna copy paste it here, and instead of stock data, macro df, and it's already localized, so we don't need to do anything here. Now full indexes is gonna be equals to pd dot date range, because we want to have both the data frames in the same range. We do not want to have different number of columns and everything, because here in macro data frame is about 400 rows, and here is about 11,000 some rows, right? So we want to keep the same range for the data. So stock data dot index dot minimum is going to be the first. Stock data dot index dot maximum is going to be the last index in the date range, and the frequency is going to be day, not the month or quarter. And then macro daily data that there are in the same range is macro df dot reindex with full indexes, and let's forward fill to remove the null values there. Alright, so now we have macro daily data. Let's merge these data with the stock data and these two data frames. So merge data frame is going to be stock data dot join. It's going to be easier to join a left join now because we have similar date format and similar number of rows there. So macro daily, and how do we want to join is going to be a left join. Okay, what happened there? Alright, sorry. Okay, so now let me show you what merged dataset we have. Now let's see, we have open, high, low, close volume plus all the macro indicators. Now if you observe, we still have those null values for all over these states, all of these dates. Now we can apply pre-process and feature engineering functions to fill up these null values and create features from this dataset now. So let's do that. So full df is going to be pre-process data, and we will pass the created feature data frame. So we will create feature here, and we will pass merge dataset with the ticker name. With the ticker name. And if I observe full df, now we have 24 columns in place of 15, and all the null values are gone. We have created log returns, rolling averages, rolling volatility, max drawdown, momentum, RSI, all those features that we have created during the maybe second video of this playlist. So now we have the full dataset, clean dataset that we can feed that into the different models that we have created. Before that, we still want to split the data, so let's do that. So let's create a function for that. Train test split data. We will pass in full data frame and ticker name. Features are gonna be every column except the rolling volatility, log return. That's what we are targeting. So log return is gonna be a target, and the others are gonna be a feature. So full df dot columns dot difference, and we will pass in the ticker name underscore log return. That's it. Yeah, and the same way x is gonna be full df features, all the column in the feature dot values, and y is gonna be full df. I'm just gonna copy this one. Full df log return dot values. Now x train is going to be used for training, test is going to be used for testing. So x train, x test, y train, y test is gonna be train test split. It sees the function that we have imported. X, the features, the target variable data, and test size is going to be 0.2, which means 20% of the data is going to be used for testing, and the 80% of the data is going to be used for the training of the model. And shuffle is going to be false. Why we do not want to shuffle? Because we're dealing with the time series data, and we do not want to mess with the time and the sequence of the time of the data. So that's why we do not want to shuffle. We will also apply scaling. We have imported min-max scaler to have all the data in one sequence, in one range. It's not sequence, sorry. So x train scaled is equals to scalar dot fit transform x train. The same way we will have y test scaled dot fit transform. Sorry, that's gonna be x test again. X test. Okay, and then return. We want to return x train scaled, x test scaled, y train, and y test. So now we have the, okay, where is that? Yeah, there it is. Now we have wait, this should be the square bracket, not this parenthesis, because it's, yeah, now we have the splitting function. So let's go on to feed the data to the models. Let's first of all call the splitting function x train, x test, y train. Okay, it's 22 minutes, that's fine. Y test is gonna be train test split data. We will pass in full df as it is and ticker. Wait, we do not want to pass in full data frame just like that. Let's drop the column and then full df as it is, and ticker is gonna be ticker because we already have defined. Anyway, and now we need to pass in input shape, not state, input shape. If you remember the last video, we talked about having a shape in input shape in deep learning model. The first thing that we do, that we pass into the first layer of the deep learning model. So let's define input shape. It's gonna be x train dot shape, the second element of that x train, and 1, and then we will pass in that input shape into model equals to build LSTM model, and we will pass input shape there. Now we are gonna need to reshape the data because LSTM Keras layers, they do expect the input shape of three dimension, which is batch size, timestamp, and the features. The batch size is going to be the number of sample, the number of rows, the timestamps, and the features, the number of feature per timestamp there. And we will need to convert the 2D data frame, because this input shape is 2D. We need to convert that 2D data frame to a three-dimensional. That's why let's reshape the X train reshape equals to np.array X train. D type is f np.float 32 dot reshape X train dot shape the first element, X train dot shape the second element, and we will add 1 to convert that to a three-dimensional array. The same way we will do that for X test. So X test reshape X underscore test. We will do X test. That is, now we can go and fit this data to our deep learning model. Is model the history equals to model dot fit X train reshape and np dot array y train. Date type is gonna be np dot float 32. Epoch is basically the number of cycle I want to train my model for. I'm gonna go with 50. Ideally I would go with a lot higher number, perhaps 100 or 500 or maybe 1000, depending on the number of rows I have in my data set. But I'll explain why I have chosen 50, because we are gonna go with early stopping. I'll explain what early stopping is, but let's keep the epochs at 50. Then we will have batch size of 32. You can experiment with lower batch size, 16 or perhaps 64. Validation split, again, it's going to be 20%, so 0.2. And here we will define our callback for early stopping. Early stopping is basically halts the training process when validation loss has not have been improved for 5 consecutive epochs. So callbacks is going to be early stopping. We have imported this on the top of this notebook again, and we will be monitoring val loss for validation loss, and the patient is 5, which means it will halt the training when validation loss has not improved for 5 epochs. If we keep it at 10, it will halt after if the loss hasn't improved in 10 epochs. So yeah, that's our model fitted with the data. Now we can do predictions using this model. ypred is gonna be model.fit we have already fitted, so model.predict X test reshaped, and it will do the prediction for us. We also need to fit in the data. If I'm just keeping the track if I'm not on the wrong path, we also need to fit the data into the other models to have the prediction from them. Yep, so let's do that. So ARIMA prad is going to be equals to ARIMA underscore baseline, and we will pass in y train. We don't need to pass in reshaped values for that. The reshaping was just for the deep learning model, and y test. And the same way, linear regression underscore prad is going to be equals to linear, and let me just make sure the function name, yeah, linear regression baseline. Baseline is again y train and y test. So let me just copy paste that here. Now we can print the comparison for of this. Print comparison. Let me just play with that. Anyway, the first print is gonna be LSTM model. Evaluate underscore model y test and y prad. We have y prad for model. So that same way we will have for ARIMA, and for ARIMA we have ARIMA prad, and for linear regression we have LR prad. So that's going to evaluate our models. We'll have the values for MSC, R squared, and others, and the backtest strategy. Almost forgot about that. So backtest strategy, we will pass in y underscore test, y underscore prad, and ticker. Same way we will pass in for ARIMA prad, and instead of ticker, let's we need to have some sort of a differentiation there. So ticker ARIMA, and we will pass in for linear regression. Which is LR prad. And eventually we do also want to plot the training process of the deep learning model. So plot dot, you know what, I'm just gonna go and copy this piece of code. I'll change the requireds at the end. Plot dot figure. Instead of that, we want to have history, and we want to plot loss. Label is gonna be training loss blue, and this is gonna be history dot loss, so validation loss, and do not want the second one. Label is gonna be validation loss rad, and let's change the line style as well, just to have some sort of a differentiation. Line style equals to dashed. The X label is gonna be a purchase, Y label is gonna be loss. and the title's gonna be model training loss over time. Right. Okay, we got the error stating that let's run this. Okay, I forgot the comma. Let's run it. Line style. Yeah, sorry, there has to be a comma. Where? Oh, sorry, that was a typo there. And fit transform. So I do have a lot of typos. Forgot S. Callbacks again, that S. Alright, let the training happen. I will see you at the end of this training process. It's gonna take a while because yeah, the batch size is not ideal and everything. I'll see you guys at the end of this training process. Alright, so the training has finished. I can see the input shape of 23 feature and 1 target variable as we printed that. I do want to mention that I couldn't get ARIMA model running. I was facing an issue with, let me show you, ARIMA baseline. This ARIMA model, in the previous video I just mentioned model.forecast, which didn't work. So I researched on ARIMA documentation. It had ARIMA results.forecast as well. So I imported ARIMA results on top here and tried that as well, but it didn't work again. So I have for now I have commented out the training for ARIMA, the results for that as well. So that, for now we're just going to be talking about the deep learning model and the linear regression model comparison. So let's see the comparison. First of all, LSTM model comparison. If you see the backtesting performance graph, the Apple log return, which is the blue spikes here, are the actual daily log returns, which are volatile, you know, and with the occasional big sort of jumps here and there, and the drops as well on the negative side. The dashed red line, if you notice, is the model's prediction, and particularly notice how it's almost a flat line at hovering around 0, right? So at the first glance, the error, you know, the mean square error, the mean absolute error, it looks so tiny. It means absolute error is of 1.37% log returns per day, but that R square error, if you take a look, minus 1,600 is a red flag. That means our model's variance is too low, that it is far worse than predicting the average return every day. So in other words, if I want to explain, the LSTM collapsed to a nearly constant forecast, missing all the real dynamics. So it didn't perform greatly. In this case, what you will do, you will fine-tune the model parameters, perhaps change the number of epochs, perhaps remove the early stopping and give the model enough time to train, perhaps change the batch sizes, and you can also experiment with the different layers in LSTM, you can change the activation function, you can change the Adam optimizer to NADM, you can perhaps change the loss function as well. You can experiment with that. I'm not going to do that in this video. I'm just letting you know that you can do experimentation to make the model better, to have better R squared score here. So that process of changing different parameters is called fine-tuning of the model, and that is also a crucial thing to learn as a machine learning engineer. Now let's take a look at the linear regression model. The red dashed line again are the prediction values, and the blue line, they're much more tight compared to the deep learning model. Even they are noisier, but they are still tighter in the earlier stages there. The mean absolute error of 7.34% and mean squared error is of 0.0149, but the R square is positive here. It's not negative like deep learning model. So that tells us the linear regression captures some of the return volatility, about 16%, because R square is 0.156, is rounding that up to 16%, whereas the LSTM capture effectively nothing, right? So in this case, I would say that the linear regression model performed way better than the LSTM model. The baseline model is performing way better than what we have thought of, right? So we thought of the LSTM, the deep learning model, would perform better than the baseline models like ARIMA and linear regression, but this happened, and the prediction values are way off. And this is the final loss over time curve. This shows the loss plummeting to near zero within the just few epochs, less than 10 epochs, right? And both training and validation splits. Such rapid convergence of any sort of deep learning model signals the overfitting or data leakage. Even though we had dropout and we had early stopping, it still overfitted the data, and in our case the model likely memorized the patterns that don't generalize to the test set. It did perform really well with the training set, but it didn't perform great for the new data that it saw for validation and the test purposes. So basically you can go on to experiment with the fine-tuning of the model, search about how you can change different parameters, change yourself, maybe change the batch number, maybe change the number of epochs, remove early stopping, and do the experimentation and see how the model performs over the time with all those different sort of changes, and see how it works, right? In the if you want me to make a separate video on hyperparameter tuning, I can make that, but what I want to do, I want to take this model and create the end-to-end pipeline of deployment using Docker and the API and the front end, having everything at once, and see how machine learning models are utilized in the real world environment. I want to do that, but if you want, I can make another video on hyperparameter tuning. I'm not sure if how long that's going to take, but I'm definitely going to be making another playlist for deploying this model, have this entire model Dockerized with the API and the front end as well. So yeah, that's it for this video. I hope you enjoyed this, and I'm going to be posting a lot more videos related to machine learning. We're going to be creating much more exciting project with different types of data, not only the financial data. So yeah, that's it gonna be for this video. I'll see you guys in the next one.